Okay, in this presentation we are going to look at entropy calculations. This is part of the information theory part of the course, discrete maths for computer science students now. So, an input source is a discrete random variable x with a four-letter alphabet A, B, C, and D. There are four probability distributions associated with x presented below. Calculate the entropy in each case. Okay, so we have four characters in our alphabet, A, B, C, and D. So what I'm going to do here is look at the four cases where there's varying probabilities for each of these characters as part of the information source. Okay, so in case one, each letter has a probability of 0.25, which is to say the maximum level of entropy, as we're going to find out. The reason for that is because no single character in that alphabet dominates. They're all equally probable. But whereas you look at case 2, we have 0.25, 0.5, 0.125, and 0.125. So in that case, we expect to see B 50% of the time, and the other three characters, A, C, and D, 50% of the time. So B is going to dominate a bit, but half the time we will see the other characters. So let's look at case 3. 0.7, 0.1, 0.1, 0.1. Okay, so in this case, A is going to dominate, more so than in case 2, where B dominated. Okay, but we still would see some of the other characters from time to time. And finally, case 4, where we have A appearing 97% of the time, 0.94, 0.1, 0.01, 0.01, and 0.01. Okay, so there, in that case, we have A coming in almost constantly with a few exceptions. Okay, so to compute the entropy for each case, we use the entropy formula for a discrete random variable x with a finite set of outcomes. So the symbol is h of x, and that is equal to minus times the summation of p of x times log to the base 2 of p of x, okay, for each of the characters. So essentially what we're going to do is multiply the probability for each character by the logarithm of that probability to the base 2, and for each character, and then add them all up. Because this will surely result in a negative symbol, we have a negation there just to actually turn it back into a positive number. Okay, so now we will compute the entropy for each of the four cases. So case 1, and again in this case we have probability of x equal to A equals 0.25, likewise probability of x equal to B, probability of x equals C, and probability of x equal to D equals 0.25. Okay, so for each of these cases what we're going to do is multiply 0.25 by the logarithm of 0.25 to the base 2. So there's four of them there. So essentially what I do is let that equal to minus 4 times 0.25 times log to the base 2 of 0.25. Basically deduplicate the four results there for the four characters. The entropy is associated with each of the four characters. Okay, so that's where we get that minus 4 from. So minus 4 times 0.25 times log of 0.25 to the base 2. Well, minus 4 times 0.25 is minus 1. Okay, and log of 0.25 to the base 2 is minus 2. So we end up with minus 1 times minus 2, which is 2 bits. Okay, now just remember when I said this is going to be the maximal value, because this has the maximum dispersion, so to speak, of the characters. Okay, no single character dominates. They're all equally probable. Okay, so that's it, 2 bits. So case 2, x equal to A is 0.25, B is 0.5, C is 0.25 or 0.125, and D is 0.125. Okay, so what we have here is minus 0.25 times log to the base 2 of 0.25, that's A, plus 0.5 times log to the base 2 of 0.5, that's B, plus 0.125 times log of 2, log to the base 2 of 0.125 plus 0.125 times log to the base 2 of 0.125. That's C and D in both cases. So, for A, we have 0.25 times minus 2. For B, we have 0.5 times minus 1. For C, we have 0.125 times minus 3. And for D, we have 0.125 times minus 3. So that is minus 0.5, minus 0.5, minus 3, minus 0.375, minus 0.375. And when we negate that, essentially, and add them all up, we get 1.75 bits. A little bit less than our previous value in case A. So moving on to the next one. So I'm going to speed this up a bit. We have probability of x equal to A is 0.7, where in all the other cases, the probability is 0.1. So for A, we have 0.7 times log of 0.7 to the base 2. And for all the other cases, we have 0.1 times log of 0.1 to the base 2. So what we end up with is log of 0.7 to the base 2, that is minus 0.5146, times 0.7, that gives us minus 0.36022. For the other cases, we have 0.1 times log of 0.1 to the base 2, that is 0.1 times 0.1 times minus 3.3219, and when we multiply that for each of the three cases, we get minus 0.99657. So we add those two numbers together, and we essentially get our answer there, 1.3568 bits. Okay, so you notice it's decreased a bit now, okay, from 2 to 1.75 to 1.35. And that's because in each case, one character is getting increasingly dominant, okay? So finally, for the last case, and we'll leave it here, x equal to A is 0.97, and in all the other cases, it's 0.01, okay? So 0.97 times log of 0.97 to the base 2 is minus 0.04258. Log, or 0.01 times log of 0.01 to the base 2, that is, log that will work out to be 0.19932. That's for each of the three cases, C, D, and B, C, and D. Okay, so we end up with minus the sum of minus 0.04258 minus 0.19932. Essentially, sum is a bit of a unusual expression there, but that's exactly what it is. So we add those two numbers together and just resolve the minus signs. We get 0.2419 bits. And there we go. Okay, so you're much lower than the first case here. This is because character A dominates massively, like 97% of the time, 0.97. The other three only get a look in 3% of the time. Anyways, just to sum up, we have case 1, the entropy of x is 2 bits. Case 2, the entropy of x is 1.75 bits. Case 3, the entropy is 1.3568 bits. And in case 4, the last one there, we have 0.2419 bits. So these values reflect the uncertainty or randomness in each probability distribution. Case 1, with equal probabilities, has the highest entropy. In fact, it has the highest entropy possible for 4 characters, while case 4, with a dominant probability, has the lowest entropy. So that's it. We'll leave it there.